All right, here we are with AP Physics vertical motion. Going to take a look at the first problem here. Problem 1, metal washers are attached to a 3-meter long string at 30-centimeter intervals. The end of the string is held up in the air by a person standing atop a table. Qualitatively describe the sound made by the washers hitting the floor when the string is released. Why does it sound this way? So if we were to go ahead and attach washers on a string, choop, 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 putting them evenly spaced here, 30 centimeters apart. And then we were to go ahead and let go of that string, right, from above the tabletop. Then you say, well, what's it going to sound like as they come down and hit? And you say, well, since they're an even distance apart, and as this falls, the only force acting on it is gravitational force. It's unbalanced force. It's going to accelerate down. It's going to be going faster and faster. So that means that as it's falling, it's going to cover each successive distance in less and less time because it's going faster and faster. And that means that as they hit and they hit the floor going ching, ching, they will hit faster and faster. The time intervals between will be smaller and smaller. So it'll be like ching, 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 right as it hits. So that is the answer to that first part. Is of course it'll go ching 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 ching, ching as it hits because it's getting faster, having smaller time intervals between hit strikes. Okay, so then part B says, well, what if you wanted this to fall and have them hit at even time intervals, even though it's accelerating down? How should you space the washers out? So I'm going to jump right to showing the answer. So what I'm going to do is I'm going to space them. And you say, well, obviously, later on as it falls, they're going faster. So I need to have them be farther apart so that they take the same amount of time, even though they're going faster. Same amount of time to hit for the next washer to hit. So they got to start spreading them out more and more, right? And so it turns out that the spacing you need, right, on the string is going to look something like this. All right, it's going to go off the top of the paper there. But the spacing you need is so that if you call this separation, just, you know what, let me squeeze another one in. And that's how I'll cheat. I'll squeeze another one in like really close there. So the spacing then, if this first distance, we call that 1, then the next distance between will be 3, and the distance between the next 2 will be 5, and between the next 2 will be 7 times as far apart as that first one had been. And then so on, and then 9 and 11 and 13, following the odd numbers, the odd integers. And you say, and if that sounds familiar to you, falling objects and odd integers, that may be because of Galileo's law of odd integers that I told you about last year in honors physics. So Galileo's law of odd integers, Galileo was looking at dropping objects and at how far they would fall in successive time intervals. And he found out that in successive time intervals, in equal intervals of time, the distance fallen follows the odd integers like this pattern. So that's Galileo's law of odd integers. But as far as why it's true, why this happens, is easier to explain if instead of looking at the distance it follows each time increment, if instead we talk about the total displacement of it at each time interval, after each increment. So after the first increment, again, of course, the total distance fallen is 1. But after the second interval here, the total distance fallen is 1 plus 3 is 4. After the third time increment, the total distance fallen now is 1 plus 3 plus 5. So, whoops, this total distance here, sorry, I wanted to do this, is 9. And then the next interval, 1 plus 3 plus 5 plus 7, that's going to be 16, and then so on. And so we are building up. Now, you recognize these numbers. You know, the next one's going to be 25, then 36, then 49. You recognize those as perfect squares. Here's why. We know this formula for the displacement of an object that has a constant acceleration. Delta x is v naught t plus 1/2 at squared. We derived this last year from looking at another object that had a constant acceleration. That was a cart rolling down a straight ramp. But in this case, for the falling object, what's the initial velocity when we drop this thing? Well, the initial velocity is 0. So this term is going to drop out. So now, and the acceleration here is just the acceleration due to gravity, little g. Well, negative g if you want to be precise. We're going down. But I could write this equation then like this. Delta x is 1/2 g t squared. We're just called down the positive direction. But the thing about this equation is, do you recognize that this here, this is a constant, 1/2 g. So the displacement is just proportional to the time squared. The total displacement is proportional to 1 to 4 to 9 to 16, how much time has passed. And so it follows the perfect squares, the total displacement. And that is why you put the washers that far apart. I have taken liberty of constructing a couple strings like this with the washers spaced that far apart. I will share that with you in class next time we meet. And that's problem 1.